Carl Dieter Christmann, he did something, but it's a part of extension of what he was doing, and it's actually going still on. What I'm going to be discussing is going to be some cycle theory of parity from this title, as you can see. So, Professor Saito gave actually very introduction about what higher child groups were in terms of motivic homology, but because that's going to be more going to be used over here. So let me briefly recall what these things were. So what are actually child groups and higher child groups briefly. So of course, people know about these ones. So X is, of course, a variety. When I say a variety, it's an equidimensional K scheme over finite type over K, but sometimes you can assume that this is irreducible or integral. So the child group of codimension R is, by definition, it's actually codimension R cycles of codimension R on X, which means that formal finite sum of codimension R's of varieties on X, and we need a certain relation which is generally called the rational equivalence. Of course, this means that so this is actually generated by things of the form divisor of R, where actually push forward of divisor of R, where so R is a rational function of some variety Y. Y is lying on X of codimension R, and F is sorry. Sorry. Maybe Q. Yes, that's important actually. Yes. So F is a normalization, and on the normal variety, you can actually take this divisor and you can push it forward. So that's actually one way of defining this. So these days, this child group has a lot of generalization. One of them is higher child group, and because this, although it's briefly mentioned, let me just say a few words about this. So there are several ways. One way was, as Professor Saito discussed, so higher child group is a way to generalize the child groups from various perspectives, and one of the ways of seeing this one is going to be regard this one as a algebraic geometric analog of singular homology, and using that kind of idea, we can actually define the stuff that actually satisfies this kind of exact sequence. So you have X and Y are smooth varieties, so this is closed, and you have a complement, then smooth of codimension, let me say D, then we generally have a child group has a exact sequence that is satisfying this. Here I just take the usual push forward of cycles that is lying on Y, regard it as a cycle on X, and this is just simply pulling back by the open inclusion. And generally this is not actually left exact, but with this theory of higher child groups, you can actually make this one indefinitely long. So you have a child, for instance, RU1 and child RX1, and there will be actually a second step and the third step and these. Okay, so that's going to be one actually step. Well, the better definition is better be actually giving a way of constructing this subject. So X is, again, a K scheme, K variety. Then this delta N is actually affine space given by the spec of this simplicial stuff. So you have faces given by TIs at 0. And this is going to be a co-simplicial scheme. And instead of, so when you do algebraic topology, then you generally take the morphisms from delta n to x, but that's going to be a really bad idea to do in algebraic geometry. So you take instead cycles that are called correspondences on this. That can be regarded as morphism from delta n to x. But this is still too big. So I take, so this is co-dimensional R cycles over here, but I take this subgroup. This is, by definition, cycles that intersect with all faces properly. And this is has then various base maps actually coming from this co-simplicial structure. So you have, so this value actually has various base maps that go to the n-1 level, and this actually goes to another like this. So this is actually going to be a simplicial abelian group. And its homology at nth level, maybe some people might call it homotopy for simplicial abelian group, which is the same thing, is by definition this high-char group. So that actually enjoys several properties. We don't really spend much time on discussing what all of these groups actually satisfy or what kind of property. And this is actually a very difficult group to study in many cases. So certain important points that one of which were mentioned in Professor Saito's talk was, first of all, in case X is smooth over K, then the higher-char group actually can be interpreted as Voevodsky's Motevic homology that are defined in terms of X groups in the triangulated category of Voevodsky motifs. And there are many other things, but one thing that I want to write down over here is going to be relevant in our discussion about the cycle groups in hyperplane arrangement. So in case I take the point, spec K, then what is very much well known nowadays is going to be this group. This is a group of zero cycles on the space of dimension R with nice properties with respect to faces. And this is going to be actually isomorphic to so-called the Milnor case theory of this K. So, of course, let me remind you of the definition of Milnor case theory. What is this guy? The Milnor was attempting to construct a general case theory, and he actually did this one, but although it is important, it was not the most general thing, but still it's actually an important part of this data. So, Milnor case theory. We can define it for more general rings, but for our purpose, it's enough for this. And this is a Milnor graded ring. And this graded ring is, by definition, the tensor algebra. So this K cross is a multiplicative group of the units of K. And I take a tensor algebra, and this is now still a graded ring. And for this graded ring, I take the two-sided idea that is generated by elements of this form. So that's going to be actually giving you the definition. Of course, this is a graded, so by taking the quotient, you still have the images of the grade n space, and the grade n space will be the nth Miller group. So that's Miller case theory. So this theorem was established by Nestorenko, Suslin, and independently by Totaro. And the Totaro's one is actually interesting in that it actually constructs explicit map and constructs all the relationship in terms of the cycles. So there's nothing actually really wrong with this. It's actually very interesting stuff. But one question that we raise out of curiosity is going to be this. So this actually higher child group uses some homological idea to define it. But what we try to ask is this: is there a kind of classical way to redefine or describe them? So here, of course, I have to explain what this classical means. That so in the classical child groups, the child groups are defined in terms of cycles modulo the certain divisor of rational functions. So here, what I try to do is get classical in the sense that in terms of certain cycles modulo simply divisors of certain rational functions. Of course, a part of this idea in over here, if you look at it carefully, then you see, in a sense, relations are coming from the divisors. But what we are looking for is going to be a much simpler formula actually to define this. Of course, it turns out it's not very simple, but at least for certain levels of this, it was actually simply describable. So what we try to do is this. So suppose I have X is a K variety, and in the usual higher child group situation, people generally attach a space, which is affine space, to X and take certain kind of cycles over there. So we still try to do it. And so over here, what I try to do is to use some hyperplane arrangements. On this AN. Of course, in a sense, this classical ones already uses certain hyperplane arrangements as faces. So depending on the actually perspective, still this actually uses some ideas borrowed from that. But here we are actually allowing all kinds of hyperplane arrangements so that they can possibly give you some extra information that were not captured in the previous discussion. So let me give you this definition, which is at this moment still provisional in the sense that if we want to get some powerful result, we might have to change the definition. But so far this one was working better than other ones that I have been considering. So X is a K variety. And suppose that A is a hyperplane arrangement on AN. Of course, this means that this is actually a finite collection of hyperplanes. But for a while, we don't really need this one, but it's just, let me emphasize that this is actually allowing even repetitions too. So that you have this one, and then what can you do with that? So I will take this ZR of X with arrangement A. So this arrangement A already encodes the information about the ambient space dimension. And that's going to be actually, so this is R codimension R cycles. So I should probably mention that this is, again, provisional yet. That intersect, so X cross, so dA, so dA means this is the natural effective divisor of this arrangement, which means that we simply take the sum of the hyperplanes and we count the multiplicity of the two. That's going to be effective divisor. And so we actually have this guy is still an effective divisor on the space X cross AN, and that's going to be giving you some criteria. So you collect the codimension R cycles that intersect this one properly, and you actually define something that looks like red. This is kind of analog of rational equivalence. And that's a little bit more complicated, but we try to imitate what was done for the classical case. So this is going to be the subgroup generated by the things that look like F lower star of divisor of Qs. But sometimes we cannot really allow all possible Qs. So we have to give a restriction like this, where, sorry. Yes. Yeah, yes. Sorry, yes. I'm very, very sorry, yes. I was about to write it, but somehow I forgot when explaining what this is. Yes, intersect this one properly, yes. I'm very sorry. Sorry? Yes. Yeah, but we ignore these repetitions over here. That's right, yes. So here, it's a proper intersection is a purely scheme dimensional, Krull dimensional concept. So it doesn't really count anything with this multiplicity. Doesn't come in at all. So the multiplicities come in over here in this, especially the choice of these allowed Qs. So where so as before, I have so F is going to be a normalization of certain variety, where so Y is going to be a codimension R minus 1 closed variety, and it's X cross AN, and Q is as a rational function Y, but what we have to do is actually that we need certain conditions over here for Y and Q as well, just like we did actually impose some conditions such that. So number one is we actually want to require that Y actually intersects also this X cross dA properly. And the second condition is a little bit more delicate. So because we don't really allow all possible Qs, so this Q is satisfying some condition. So Q satisfies. Oh, by the way, I just regard this Q as a function on this normalization. And just without actually, I'm not going to write it down. This pullback of Q satisfies the condition that so the divisor of 0, not the full divisor of 0 minus 4, but the divisor of 0 of Q minus 1 is actually bounding the pullback of so if I have a hyperplane H in this arrangement, then I have a multiplicity MA, so this is an integer, and I actually pull back this effective divisor, MH. So this is going to be a effective Cartier divisor on this. And you can compare the divisor of 0 over q minus 1 with this. So in a sense, what you can see is this looks like a little bit artificial one. What this one actually means that in case it is actually intersecting with this hyperplane H, then the intersection shouldn't be random. It is actually intersecting in such a way that it is always bounded by the points where it actually attained the value 1. So in case there is no point that attained the value 1, then this one should not actually intersect at all. So that's actually one of the delicate parts. So this looks like a rather artificial kind of thing, but because we have imposed some condition, we have to make use of the assumption that we are making use of hyperplane arrangement. And actually the second one is actually the one that uses this. So I have these cycle. Sorry. Yeah. Yes.
This is a group.
I'm going to be quotienting it out. I'm just a subgroup generated by this. Yes. So, I mean, if we collect only those things, it's not necessarily a group, but we can just generate, so use them as a generators. So I define, because this is not necessarily the group we are looking for, so let me just use this provisional letter. Instead of CH, I will call it AH. So of R and X, and the arrangement A is simply the by definition, this cycles with respect to the arrangement modulo the rational equivalence analog of this. So we might probably wonder if this one has some interesting properties. And there are actually various interesting properties. So one of the actual results is going to be, so objective over here, because it was just defined only very recently, this is still going on. So objective in this talk is actually to discuss what happens in the simplest possible case is when X is spec of K, for instance. So if X is spec of K, and also R is going to be equal to N, so that we are basically dealing with the 0 cycles. So that's probably the first problem to attack if we define a new thing. So here what we try to do is to calculate this AH with N and K, and this arrangement A, where A is a hyperplane arrangement on this affine space for various and actually hyperplane arrangement turns out to be actually much more complicated than actually I was thinking about. It was initially very naively attacking this one, and then hyperplane arrangement itself has a lot of geometric problems associated to it. So I actually picked certain natural candidates for this calculation. So the first thing that I'll be working with are actually going to be so-called polysimplicia spheres, or maybe polysimplicia arrangement. So let me just tell you what these things were. Oh, by the way, before I talk about this one, there is one interesting result that tells you that the hyperplane arrangement should be actually at least satisfying some minimal property to be able to have a non-trivial group. So here is one brief remark, is that, so suppose for the simplicity, X is spec K, and R is of course N. Then suppose that, so let me define the rank of the arrangement A to be the dimension of the span of the normal vectors of the arrangement H contained in A. So regard this affine space as a vector space, and you can actually consider this rank. And so one thing that we can calculate is that, so if rank is too low, this is very, very bad actually problem. So if the rank of A is less than the space dimension, then this arrangement child group, for instance, that we are trying to calculate, becomes just 0. One actual reason why this is happening is that if the dimension of this, the rank of this space is actually too small, then suppose we have, well, this is 2, the dimension is actually, so suppose I have only one hyperplane arrangement over this 2-dimensional space. I have a bunch of cycles, for instance. Then I can always actually find some point where this is very misleading picture, but if the dimension is actually low, then, the rank is low, then you can always find a certain kind of line actually that passes through 2 points without actually touching all of the given hyperplane arrangement because of simply the dimension reason. So, but the very fact that we can actually connect these 2 given arbitrary points by a line actually give you some rational function Q that actually have a vanishing value over here and there only. So basically, you can identify any 2 given arbitrary points. So that's going to be actually telling you that at least the rank of A should be equal to n. So otherwise, the arrangement is very stupid, so that you don't really get something interesting out of this. But this polysimplicious sphere is going to be interesting enough one, and I want to tell you what this one is. So polysimplicious again. So polysimplicious spheres. So they are generally the most trivial cases, just like over there. So for instance, a simple example. In the case when n is equal to 2, yes, when n is equal to 2, then I have a plane. Then what I can try to do is to consider certain faces that are coming from over there. So you can have 3 faces over here and there and there. And I call it actually sphere because over the real points, you actually have only one connected bounded chamber. There are actually unbounded ones. It's actually algebraic difficult to capture, but over the reals, topology says something about this topology of this complement of the hyperplane. So the complement of hyperplane arrangement has connected components that are called chambers, and these chambers, how many actually bounded chambers are there is actually very, very interesting, important invariant for complements of hyperplane arrangement. So this is what we are going to be calling so S2. So S2 is going to be called, this is a usual 2-dimensional simplicious arrangement. But I think I shouldn't actually erase this. N is 2. So S2. So S2 is the collection of hyperplanes on that are given by, so suppose the affine 2 space has a coordinates T1 and T2. Then T1 is 0, and T2 is 0, and the T1 plus T2 is 1. So that's going to be, so this is these pictures. But this is not the only form we can actually imagine. So we also have, just like there is also a different version of child group called cubical higher child groups. And over there, this 2-dimensional one is also having some analog. So also in affine space A2, we can consider the coordinates T1 and T2. And you can consider T1 is 0 and T1 is 1. And T2 is 0 and T2 is 1. So there are 4 hyperplanes. And pictorially, this means you have, so T1 is 0 and T1 is 1, and T2 is 0 and T2 is 1. So again, if you look at the complement of hyperplane arrangement over the reals, then you have actually only one bounded chamber for this case. So in general, you can actually do something more general. So we can define actually the following kind of thing. So we define the polysimplicial sphere which is, let me write it as S of D1, D2, up to DR. Whereas, without loss of generality, I can assume that this is this kind of non-increasing sequence of numbers. And here I have a bunch of coordinates, and here n is going to the sum of these numbers. And you can consider the situation like this. So I have Fn space with the coordinates T1, T2, but for the sake of discussion, let me artificially write it as T1, T2 up to TD1. So this is the first group, and you have TD1 plus 1, TD1 plus 2, up to TD1 plus D2. So this is the second group, and so on. You can go on. So you can define the faces by the equations. First of all, T1 is 0 and T2 is 0 up to Tn is 0, so as before. But let me define Fi to be the sum of the ice group coordinates, the sum of ice coordinates, which is Tdi plus 1, Tdi plus 2, up to Tdi plus Di plus 1. And you take the faces, these guys, together with the Fi's are equal to 1. So in this, so sorry, yes, so this is D0. So that's right. D0, 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 that's a D1. So maybe F1 is, okay, sorry about this. F1 is, this is confusing all the time. Especially when I'm giving talks. So this is D1, and do the same for Fi's similarly. Okay, sorry about that. Yeah, so it's a sum of the ice coordinates. Yes, index is always very confusing. Yeah, so we have, so essentially you have this SD1 up to DR has precisely how many hyperplanes you have n plus all hyperplanes. All of them are reduced. So actually this is actually very interesting, and as the definition suggests over here, these polysimplicial spheres for n fixed, so n is fixed, is actually in bijection in one-to-one correspondence with integer partitions. Of n, so here, and that's actually corresponding to the weight and Young diagrams. So you can actually easily draw some pictures. For instance, I can give you 3 pictures when n is 3. So when n is 3, for instance, so we know that n has various partitions of integers, so n can be written as 1 plus 1 plus 1, but in terms of Young diagram, that's corresponding to this. but n can be also 2 plus 1, which is corresponding to, we have 2 boxes and we have 1 box. And n is 3. It's awkward to write 3 is 3, but that has some meaning, which is this. And each of them actually corresponds to hyperplane arrangements. And pictorially, this is actually corresponding to tetrahedron. So each of these actually faces actually corresponding to the respective hyperplane, and you actually have only one bounded chamber over the rears. And here, of course, this guy is, maybe this is more instructive. This is actually a cube. And this fellow is, if you think about it a little bit, then you realize that this is going to be a prism kind of thing. And what is actually interesting is that over the rears, you can, this is exercise, maybe. So over the rears, if a hyperplane arrangement on AN has a unique bounded chamber, then actually A must be affinely isomorphic to these guys for some integers. So over the rears, it's actually it's not completely trivial, but if you think about it a little bit, then you realize this is actually what you get. So in a sense, this is a very interesting data because this is giving us some clues about cubical higher Char groups. Affine, yes, I said affine isomorphism, affine. And this actually gives some clues about simplicial higher Char groups. But this is actually now corresponding thing. But the definition that we have given over there can actually explain something about this too. So the first theorem we can actually prove is going to be the calculation of the arrangement hyperplane arrangement Char group. The theorem number 1 is going to be that if A is affinely isomorphic to SD1 to DR, so essentially we can regard it as a sphere just like these guys. Then, so with n is D1 plus all the way up to DR, then if I calculate the zero cycles of the Char groups with respect to this arrangement, and that's going to be actually isomorphic to the Milnor K group. So it's not in a sense kind of generalization of Totaro and Nestorenko-Suslin because it's completely different object, but we just obtained the analogous result. So actually, this result was obtained in a similar framework for the simplicial version by Nestorenko-Suslin and the cubical framework in the Totaro, but still that's actually in terms of higher Char groups. But this is a different object, but somehow we can prove that they are isomorphic. So indirectly, this implies that this arrangement is in the simplicial sphere, polysimplicial sphere case. It's actually isomorphic to the higher Char group for all of these kind of polysimplicial spheres. And the proof of this one is not something that we present in talks like this. It's a little bit too messy. But so out of curiosity, no, we actually can construct a direct map that actually give an isomorphism. So of course we have to do a lot of things. We can the point is not necessarily K rational, so we have to do a lot of construction of K trace maps and all these compatibility of trace maps with this the Kato's boundary maps and all these, which is very much similar, by the way, to the work of Totaro. But essentially, we have to use some cycles that are used in this Totaro's calculation, plus some other cycles that are actually coming. So this is analog. Yes, yes. By definition, no, it's not, because in the cubic hierarchy group, actually boundaries are coming from one higher dimension space. This is actually in the same space. That's a problem, yes. That's a difference. So that's a major kind of issue. So we have to redefine. So on the level of cycles, the maps are same. Whereas on the relation part, we have completely different thing. So it's not clear whether they are isomorphic from the first place. But from geometry, if mathematics is beautiful, that should work. So probably I was believing they should work. It did work. And the proof isn't very difficult. Once people master these proofs of Nestorenko, Suslin, and the Totaro, then this is probably one interesting exercise that one can sit down and do several days. Then that's not very complicated. But curiosity actually encouraged me to work further. So what if A is kind of degenerate? So of course the degenerate, I didn't define what degenerate and non-degenerate means, but so maybe I have to give you a definition. The definition, so arrangement A on AN is non-degenerate if, first of all, it is reduced. Reduced means the multiplicity is 1. Number 2, it is actually of full rank, because otherwise it gives nothing. But there is something that we call locally linearly independent. So that means that at each point, if you collect all hyperplanes that pass through the given point, then the normal vectors should be linearly independent. So for instance, in the plane, this is the S2, but at every point you have linearly independent ones. But if I move this guy to over here, so that I have this kind of situation at this point, then it's overdetermined. There is one more vector. So that kind of thing is violating this. But so this is actually silly. So if I drop this condition, the problem becomes too trivial. So this isn't necessary. However, if I forget about this reduced assumption or locally linearly independent assumption, then something interesting might happen. So that was actually something that I was trying to understand. And very excitingly, there are some analogs of theorems of Totaro and Nestorenko Suslins. And I have only like 15 minutes, so I cannot really define all of them. But so there is a notion called the additive higher Char groups. They're actually kind of like a degenerate version of the higher Char group. And that's actually defined in a little bit different way with some delicacy. But in a sense, you can actually interpret these additive higher Char groups as some hyperplane arrangement kind of thing. So in the simplicial case, I said the exact same picture. So over here, I use this S2, but I can degenerate this guy and in the process of taking this guy to the limit. So I have this kind of thing that I will call Q2. And this fellow, so it's actually, this kind of version was first defined by Blog and al., and they calculated this. So the Blog and al. actually calculated this additive higher Char group. Let me just use this notation of just a 2 is actually calculable in terms of the absolute Kähler differentials. Under the assumption that characteristic of K is not different from 6, maybe some very low primes. But actually, you can give a uniform interpretation of this theorem for the child group associated to the hyperplane arrangement. So this new theorem that's actually related to analog of this one is going to be that suppose I take this A to be Qn. So what is a Qn? Qn is arrangement that's on AN with the coordinates T1 up to Tn, and the arrangement is given by T1 is 0 up to Tn is 0. But instead of taking sum of Ti is 1, I take the sum of Ti is 0. And again here, you can calculate this hyperplane arrangement analog of the child group. So then this child group of this Qn, without really changing the definition, it's actually isomorphic to this omega 1 kz. So of course, again, over here, on the level of cycles, they are in the same space, but the relationships are actually different. So it actually indirectly shows that this is isomorphic to those. And of course, further excited by this thing, there is now there's a cubical additive higher Chow group is going to be something that is depending on this kind of idea. So I consider again now the cubical arrangement cubical arrangement 1, 1. I have 4 faces, but I can take this face to be collapsed to here, but leave the rest of them actually unchanged. But I can do a little bit more things. So suppose I can take something called the ENM. So ENM is an arrangement on AN. And here from T2, T3 up to Tn, I take 0 or 1. So there are actually 2n minus 2 of them. But for the first coordinate, I take actually, well, so with notational views, I will say with the power of this one is actually 0. So that means the m copies of T1 is 0 is actually introduced. So that actually has 2n minus 2 plus m bases. And that's a hyperplane arrangement. And it was very interesting that so there is actually an analog of this for the cubical algebra. So theorem, this is by Kai ruling. And he proved that this cubical additive higher child groups of this cycle n with a k and this n with some kind of number m, which is relevant to that, is actually isomorphic to the Durham-Witt complex of the Hasselholt and Larson with n minus 1. So that was actually his theorem. So apparently, so this is actually using different relations, but we can actually imitate that procedure, and you simply just use the cycles modulo divisors. So here there's another analogous theorem that we can actually prove. So this arrangement, if the arrangement A is this, so it's basically cubical with only one face collapsed into a degenerate thing. So you can have a non-reduced situation. Then this arrangement type of child group, ENM, is also actually isomorphic to the length m minus 1 Durham-Witt complex of this. And what is actually exciting about this one is that so over here we can define these Frobenius and Versiebung and all kinds of these operators. Over here, the geometric analog of the Versiebungs and Frobenia are actually very similar, simpler, much simpler than the ones that are actually given over there. Of course, that's simple over there, but it's actually geometrically. So, for instance, here we have a degenerate coordinate. So I have, for instance, A1 to A1. I have a map that I call psi r, for instance, I will send x to x with the power r, where r is a integer. Then the Verfügung is actually defined by actually cycle. It's not quite pullback of in terms of cycle theory, but I will just abuse this notation to call it pullback anyway. Yes. And the Frobenius is actually given by the push forward of cycles. And you can prove various compatibility conditions. And the proof of this one is, so we can construct a map that goes over here. Inverse map is generally coming from the universal property of this drum-width complex. So, so this actually encourages a lot of actually activities that I've been interested in. But there is, it looks like this is very, very good. But there is one little problem with this kind of discussion about arrangement. So let me just tell you one issue. This group is looking good for zero cycles, but it's not very good, actually, if I take higher dimensional cycles. So as is, so that's why I was actually using this notation AH rather than CH. The problem is, so for zero cycles in the what is called these over range is min-node range. So this is the whatever notation, simplicial, cubical, ordinary, or additive higher Chow groups. But the dimension actually bigger than 0. This is too big. So it seems that in general what we have is you have these Chow groups where R and X n, for instance. This actually maps to these AH are xn, xa. So suppose that A was chosen in a compatible way with the one that was used. If this is a cubical one, then I take the cubical one here. If this is a simplicial one, I take the simplicial one. So there's a natural map kind of thing. Highly believable that it is actually injection. However, subactivity is too much to expect. So subactivity is actually not even conjectural. It is actually not true. So for zero cycles, we don't have a problem because from the zero cycles, there is no boundary maps. Everything is in the kernel of the boundary. But over here, we don't actually take the process of taking kernel. So here is one example why this is really not true. So for instance, if X is just like the same situation you do for the localization sequence, I take the smooth varieties. This Y is closed in X. This is open complement. Then higher Chow group satisfies some localization sequence. The Chow group is actually on the right-hand side, but these additive and the arrangement ones are bad in that this actually is true, which is not what we want. So this is pretty, but it's not actually very good. This is actually one evidence that it's not actually the correct thing to do. So for a general hyperplane arrangement A, I have no idea how to actually extract information from that. But actually for the regular ones, like a cubical or simplicial ones, I can artificially define some, by imitating the definition of the usual higher Chow groups, the definition of the thing that is inside. So I can artificially define, at this moment, this is also provisional in the sense that the AH is provisional. So I can define this if this arrangement is either Sn or S11 to 1, this Chow are XA to be the subgroup in AH, Rx A, which is actually the kernel of the maps. That goes to, so here A can be restricted onto one of its faces, fix one of them when we identify this one. So the nice thing about this simplicial and the cubical one is that this is kind of self-similar on the restriction onto faces. So I have these guys arrangement on AN, but I can restrict them onto this. Here is A, and here is a restriction. And H is actually one of the hyperplanes of A. But if I restrict this arrangement to here, then suddenly this becomes Sn minus 1. Here, this becomes 1 less. But for the general intermediate polysimplicial arrangement that corresponds to these Young diagram, do not enjoy this property. So that's actually why we have to restrict this one. But we have various faces, and you can take the alternating sum, and we take the kernel of them. So this is actually rather provisional one. And then this is actually rather simple actually to show that artificially this is probably the right thing to do. But at this moment, I didn't quite like this approach of using the framework. So I'm looking for what kind of things I can do. But still, that actually gives you some clues about potential interesting problems. So, for instance, one problem that I've been attacking was the case where if A is even more degenerate, so you have multiple number of hyperplanes with multiplicities, is very non-reduced. Then, so can I calculate this kind of thing? So for instance, in the previous picture, I have taken the limit, this guy as goes to this. I have such multiplicity, but I can take this guy as well to go over here. So I have double face over here, a double face over here, and all other remaining coordinates are actually the regular cubical ones. But this actually seems to be actually giving some clues about some potential generalization of the Durham-Witt complexes. Because the Durham-Witt is, in a sense, as it is given currently, is univariate. But there is a strong feeling that there should be actually a multivariate analog of this Durham-Witt, which was not very simple to define. I was attacking it for a while, but it seems like there were some sloppy things that was not making things work. But I believe that there should be some kind of interesting thing that actually make use of 2-variable case or 3-variable cases, and then I can probably test if that is working very fine by calculating this in terms of this. And so that seems to be actually one thing that I'm trying to do, but that's actually not the one I was able to prove yet. So I think my time is up, so I will stop here, but I just reported that there was an interesting thing I found about hyperplane arrangement.
There are some questions.
Yes.
So for a non-linear case,
Yes.
the inequalities is
I don't think it's true. Homotopy invariance seems to be false, but false, yes. But I think still this.
for this Miller case.
Oh no. So for non-degenerate case, non-degenerate case, I think probably it might be true. I wasn't actually attacking that direction. For the degenerate case, it's definitely false. Yes. That's right. Yes. But for the non-degenerate case, I think so. I didn't have the time to do it, but just I think that just following Fulton's book as a very hard exercise, I think I can do it. So I don't think it's difficult problem. Just for a non-degenerate one, I expect that A1 homotopy, of course, X should be smooth. But then I expect that this is A1 homotopy invariant. So I have to develop an intersection theory over here. So there is actually a way to intersect cycles, and there is actually a notion of, so the problem over here is that there is something concatenation going on. So if I have arrangement in A and B in different spaces, there is a notion called orthogonal product on a bigger space. That's actually developed by Charles Weiber. It was 1980. And he abandoned this one, but it was, and using this one, I can actually develop some intersection theory. And then I can, for the non-degenerate case A1 homotopy, I expect it to be true. I wasn't able to prove it. This book is not very thin. But just following the argument, I believe that should be true. Also, I think moving lemma is probably true. And I don't see any problem in proving that, but just matter of writing is different thing. So I didn't verify this one yet. Yes. I expect that that's actually something that I have to do, yes. That's a very interesting problem. So I was a little bit fascinated because recently I was concentrating on this aspect. That doesn't seem very easy. So maybe I have to go back to more classical case and do something.
Other questions?
Yes.
Yeah. So does there give you a new description of Nunaki group?
Yes.
Does it give some more new structure?
No, it doesn't give a new structure. Just so it turns out that actually this, if I have this decom A of actually S D, so what is actually true is, maybe it's better to explain in terms of this one. So what I found out was that just SD1 of the DR turns out to be just the orthogonal product of D1s. And this is kind of like a prime decomposition. It is the irreducible invariance. And this actually orthogonal product is actually compatible with the product structure Miller case theory. But on individual levels, this is just trivial case. So it's just not, it just says it's compatible with this Miller case theory product, but that doesn't give any new information about Miller case theory. So, yeah. So the giving map backward was also possible. No map. Finite extension. Yeah, there is a finite extension map, yes, but the. Right. Oh, yes, of course. Yeah, that's right. I don't think it's simple. It's more complicated. It's more complicated. I don't think. I use this reciprocity proven by Suslin and Kato, but. I don't think I tried ever thought about that direction, but probably I will try sometime, yes. But I don't actually have some clues about how to interpret it yet. I see. Okay, I see. I will think about this problem. Yeah. Yes. Yes. Differential is actually pretty simple. So I have A1, and this guy actually goes to A1, because A1, I have the diagonal map, and actually this pullback of diagonal gives you differential, which is very nice. Yes. Of course, I can take a twist a little bit. I can send, if I like, x to x, 1 over x, but eventually we will be taking some kind of log, so it doesn't really matter. It just gives a minus sign. But essentially, it's diagonal map. A pullback of a diagonal, yeah.
Maybe I can also ask one question.
Yes.
So in this old definition of the Ramvet of Spencer-Bloch, where he defined it as tangent space of algebraic K-theory,
Oh, yes.
is that related to your comparison isomorphism? It seems quite similar in
It's
flavor.
very ancient language of typical curves that I don't really use these days. But
The flavor is quite similar somehow.
but I think it's related. But I don't think I even look back these old papers. But conceptually, these guys have to capture tangent space of K-series, and they are indeed part of tangent space of K-series. So I will say it's related, but I didn't explicitly write down the clear correspondence between these.
Okay, so should we restart in 15 minutes again? Or 10 minutes? Okay, 10 minutes.
Okay.